let me thank the organizers for including me in this very exciting meeting. Already in 1.5 days, I have found so many talks which are stimulating and also useful to me in the kind of problems that I have been working, for quite some years. So what I'm going to talk to you today about a notion called optimality of measurements. This was an idea that was introduced by Wouters and Fields some time ago. And at that time, they analyzed what we may now call standard tomography, and they obtained some very interesting results. And when weak measurements became very popular, I was wondering whether there would be an analog of something like this for weak measurements too, because in standard tomography you use several observables, and optimality, as they proved it, was when the eigenvectors of the different observables form the so-called mutually unbiased basis. But in weak value tomography, you use only one observable. So the question is, where is this additional freedom? And that naturally is supplied by the post-selection. And therefore, a result which I conjectured some time ago was that the post-selected state, when it is mutually unbiased with respect to the eigenstates of the chosen observable, there would be an optimality in the sense of Wouters and Fields. For qubit, this was fairly straightforward to prove, and beyond that, it became quite difficult, tedious calculations. But in the end, everything is very beautiful and transparent, and so now you can just take home the results and do whatever you want, And we have done all the hard work. This was done with a very bright student, Rajat Krishna, who came to spend a month with me as a winter research student. He is right now in Imperial College. And first we proved it for few states, and he kept pestering me to extend the results to mixed states, which I did not find very interesting at that point. But just to satisfy him, I worked on it too, and today only in the archives, our results on the mixed states have appeared. So these are the two references. The first one is on pure states. Second one is on mixed states, which appeared in the archive today. So let's take a quick look at standard tomography, which is a fancy word for determining an unknown state through certain optimal set of measurements. So we represent states by density matrices, and we only deal with finite dimensional Hilbert space cases. So a density matrix would have that kind of a form, where Ti are a set of Hermitian observables. And at the moment, we won't say anything about what the trace Ti Tj is. And in fact, we keep that as a free variable and find those Mijs for which the measurement becomes optimal in a sense that I'll describe shortly. So now, what does one do? One measures expectation values of this Ti in rho. It's very simple arithmetic. If you call them xy, then it is just mji times ci. Forget that comma. So this can be inverted to get c as a function of x, which means you'll get rho as a function of x, and x as the measured expectation values, and they uniquely determine rho, provided you measure sufficient set of observables. So that is standard tomography. A very important concept in our work is the geometry of the state space, and there are many ways of dealing with this. We start with the introduction of a metric as trace d rho dagger, and from the previous relation you can express d rho in terms of dci, complete this calculation, and you get dl squared to be gij dx dxj. So gij is a metric on the state space when expressed in coordinates which are the expectation value of Ti. The volume element standard Riemannian geometry, square root of g times product of the differentials, and I have a few more words to say on geometry, that if you first let us focus on mixed states, then it's quite clear that the matrix elements of the density matrix themselves can be taken as coordinates. There's absolutely no problem, in which case that metric is quadratic form, constant coefficients would represent a flat metric. But you have to be slightly careful because the n squared elements are not all independent, and they have to satisfy trace rho equal to 1, and usually constraints can introduce curvature, but it's quite elementary to see that this one does not introduce any curvature. So you eliminate one of the diagonal elements of the density matrix and re-express that metric in terms of the independent components, and that still maintains a quadratic form with constant coefficients. So the space of mixed states is flat. Okay. Tomography introduces different coordinates instead of the matrix elements of the density matrix itself, but the metric is still flat as long as this Mij are state independent, because then again the metric that you get after substituting in terms of the new coordinates is quadratic form, constant coefficients. But for pure states, the story is completely different, because there rho square equal to rho is the constraint, and this is a nonlinear constraint, and it generally introduces curvature, and we all know that the geometry of pure state space is not flat. And in fact, I'll tell you what the geometry of that is in a moment. Now, with every measurement, there are errors, and for Wouters and Fields took these to be the statistical errors, which are given by the variance divided by square root n, where n is the number of measurements, not the dimensionality of the Hilbert space. Sorry, I've used the same symbol here. Then you can construct an error parallelepiped. So in each direction, you take the extent to be the statistical error, and for a generic state, you will get a parallelepiped, and the volume of that is simply square root of g, which is the volume form, times the product of the extents. And now here comes the definition of what Wouters and Fields meant when a measurement is optimal. They said a measurement is optimal when this error volume is smallest with respect to the choice of the observables Ti. So the technical problem is to start with a set of Ti, find out the metric on the state space, compute this error volume, and then find the set of Ti's that will minimize this set. So in general, both the metric and these errors are state dependent, and what is optimized is really the Wouters and Fields, they optimize the state averaged error volume, which is slightly unsatisfactory feature of their treatment, but that's the best that they could do. And in fact, they didn't even optimize the state average error volume. They actually optimized something called information, which is the negative of the logarithm, negative logarithm of the error volume. And for technical reasons, they found that optimizing this is much easier than optimizing the error volume. So what is the main result? The main result, beautiful, that the set of Ti's that will optimize this error volume or the maximize the information are the ones whose eigenstates form what are called mutually unbiased basis, a concept introduced by Schwinger long ago, and it has had a tremendous impact, in many different contexts. And in fact, you could spend your whole life investigating the properties of mutually unbiased basis. So that's the result. So now I come to weak tomography, and I want to make a clear distinction between two types of weak tomography, which in the literature sometimes that distinction is not made, and both are called weak tomography. The first one is weak measurements without post-selection, and the second one is weak measurement with post-selection. The latter we will call weak value measurements to distinguish it from weak measurements. Now, weak measurements are very noisy by their very construction, and after each measurement, the input state is only very slightly changed, and that is the characteristic of the weak measurement. In the projective measurements, that is the strong measurement, the reading of the apparatus is directly correlated with one of the eigenvalues of the observable, and this is all standard and well-known stuff. But in weak measurements, this is not true, that the pointer reading cannot be associated with any eigenvalue. Nevertheless, if you average all the pointer positions, you get exactly the expectation value of the observable as you would get in strong measurements. So this way also you can measure expectation value of observables, and you can carry out tomography just as in the case of the standard tomography case. But there's one very major difference, and this will play an important role for us, is that the variance is largely dominated in weak measurements by the noise, which is very large, and there is almost no sensitivity of the error to the state. So it is state independent, and this will change the analysis in some very important ways. Now let's turn to weak value measurements, which are ones where there is a post-selection. So you take some observable, and for the moment we are only going to deal with pure states. So it's being measured, its weak value is being measured in the pure state psi, and it is post-selected by another pure state B. This is the classic work of Arnaud and collaborators. So the weak value is given by this expression. Now, what is special about it? It is invariant under psi going to e to the I theta psi. Therefore, the weak value actually lives on the state space. So it's an observable. We are told, at least I was told for a long time, the probabilities are the only observable content of quantum mechanics. That's not true. Weak values are also observable. They're observable in this technical sense, but they're also observable in the sense that you can set up an apparatus protocol where the apparatus actually registers this value. So you can read it off. So it is observable in both technical and physical sense. Okay. Now, it turns out, of course, Dirac, it turns out he has thought of everything. And this kind of a object, both Dirac and Kirkwood had thought of earlier, and they're called quasi-probabilities. And unlike other quasi-probabilities like Wigner distributions, these need not even be real. But the fact that Dirac had already thought of them, probably means that he, without commenting too much on it, appreciated their importance. So let me illustrate very quickly with qubits. So take a pure state, and this plus minus are the eigenstates of some observable, and you can expand it like that. And now we take projectors. In this case, there's only one independent projector, and you calculate the weak value of those projectors according to that formula, and it's elementary to show that B plus minus are these overlaps, psi plus minus are these alphas, and then you can invert it and solve for alpha plus minus in terms of these ratios, z plus minus. There should be a phase here, which I unfortunately have left out. So modulo a common phase for both alpha plus and alpha minus, which is physically irrelevant, you can determine the state by determining the weak values. So this is a state reconstruction of a different kind than standard tomography, and that's why this is called weak value tomography. Okay? At this stage, this post-selected state can be arbitrary, even though Lundin and Bamber, who actually gave this schema, they had taken B to be already mutually unbiased with respect to plus minus, and that is because under those conditions, this formula become very simple. So their motivation was only one of algebraic simplicity and no deeper reason. But I want to show that this condition has a very deep meaning in terms of optimality of measurements. And of course, because of the completeness, if you add the two weak values, it has to be 1. So in the qubit case, there's only one complex number which is a weak value. And in the general case, there are n-1 independent projectors, and therefore you'll get n-1 complex data, which is exactly the correct number for fully determining pure state. Okay? So now let's take W plus to be the independent coordinate. The density matrix now will be expressed in terms of W plus, and we can go back and work out the metric in terms of W plus. So this is we will use complex coordinates because that is the natural coordinate. It's naturally a complex manifold. You don't have to artificially pair two real values to get a complex coordinate. And this complex coordinate is globally well defined. The conditions under which such things can happen, are well known. Complex structure. So the metric in complex coordinates typically has this form. And when we did the calculation, we found WW and W bar components to be 0, and I'll tell you the meaning of that in a moment. And we also found that the remaining GW W bar is of this form. And since these two are 0, the metric is conformal. So the qubit state space metric, when expressed in terms of this weak coordinate, is conformal. And conformal metrics have very nice properties, and therefore this is something, bonus that we get from this. Of course, to check everything is okay, we computed the volume, and it comes out to be the 4 pi, which is the surface area of the Bloch sphere. And you can compute the error now, volume, which is, there are two directions. Errors are epsilon, they are state independent, and calculation gives the state averaged error volume to be this. Now we have to minimize this. B plus square plus B minus square is 1, it's a very elementary variational problem. And you find that the solution is B plus square equal to B minus square equal to half. That is precisely the condition for B to be mutually unbiased with respect to the plus and minus states. So we find that in the weak value tomography also, the post-selected state, when it is mutually unbiased with respect to the eigenvectors of the observable, the measurement is optimal. We went to the spin 1 case, everything becomes harder, instead of the simple Pauli matrices, you have the Gell-Mann matrices, etc., etc. But, my student was very, energetic and a lot of stamina. He also made a lot of mistakes. So I also had to have a lot of stamina to keep correcting. But we kept at it, and first result he produced was, again, these components vanish exactly as in the qubit case, and now we understand what that is. This is just the reflection of the projective nature of the state space. State space is not Hilbert space. It's because of the ray representation. It's the projective Hilbert space. And in projective Hilbert spaces, these components of the metric always vanish. But the mixed components do not vanish. And after some inspection, we found that they can be expressed as the double derivative of some scalar quantity. And I'll tell you the meaning of that in a moment. We computed the volume, which is 8 pi squared, and this is not the surface area of any higher dimensional sphere. So in the Q-trit case, it's no longer area of a sphere. Now, I'll tell you how we went to arbitrary spin. We were not even hoping to solve the spin 1 case when we saw all the algebra, but after doing the spin 1 case, the divine revelation hit both of us. And important point is the non-vanishing metric components are mixed double derivatives of a scalar function. The determinant of the metric, which also we calculated, rather Mathematica calculated it, was essentially the scalar function. Now, I had forgotten what I had learned about such manifolds when I was a practicing high-energy physicist. And these are called scalar manifolds. They're complex projective spaces. And the point is, they are specified by one potential called the scalar potential, and its double derivatives give all the metric components. And now, using the qubit in the spin 1 case, we could determine the scalar potential for arbitrary spin, including all the normalizations. So everything you wanted to know about the geometry of this space in these coordinates is immediately available. Since the chairman has signaled that I should go fast. So this is the volume element for the general spin case, error volume, and now you have to compute the total volume, which after some amount of work, again because of the magic of scalar potentials, you can analytically solve it. And the interesting thing is that the volume for spin j is 2j to the 2jth power of the volume of the qubit. And those of you who are familiar with the so-called Majorana representation will make a connection to it. Particle physics, we use the word Majorana representation for something totally different. This shows the distance between the two communities. And there is something called the star representation for arbitrary spin. You can write it as a symmetrized tensor product over qubit. But what is not clear there is whether that construction is global or local. But since the volumes match exactly, this has to be a global validity. So that was one of the side results. Optimality, so this is the error volume, you minimize it, and you find all BA squared to be 1 over n, which means that the post-selected state, even for the arbitrary spin case, is mutually unbiased with respect to the eigenvectors of the observer. Now I come to mixed states. Please give me 1 minute extra. Otherwise, I may get mixed up, So weak measurements, as we already saw, give the same expectation values. Therefore, even for mixed states, you can use weak measurements, determine the expectation values of all observables, and do tomography. It goes exactly like the standard tomography. But the errors dominated by noise are state independent. So now the error volumes are also state independent, and that little unsatisfactory feature in the Wooters fields calculation, namely where they have to state average, need not be done. So without doing any state averaging, for every state, you can prove the optimality of these results. Conclusions about MUB remain the same. Now, you can stop at that, but people never stop at anything. So Lundin and Bomber, they came up with a scheme for a mixed state analysis where they wanted to follow the pure case as closely as possible. So instead of just a projector, they considered these concatenated projectors where this is the ith eigenstate projector, this is the projector for B, and there is no post-selection here. Okay, that's important. You compute, there are exactly n square minus 1 Hermitian observables. You compute the expectation value, and that's directly proportional to the matrix elements of the row, and therefore they called it direct measurement. But even standard tomography is as direct as this. But here, the nice thing is there's only one term in this proportionality, and which means that the metric expressed in terms of rho and the metric expressed in terms of these weak values, they're related by a simple scaling, which is constant. And so volume and everything can be worked out. And once again, you can work out the optimality condition. That's the MUB. Last point is, can you do weak value tomography of mixed states? Senjung Wu proposed one. He takes, as in the pure case, starts with projectors, but he takes J post-selected states, and then you compute the weak value. They exist, and they're measurable. But when you try to do tomography, there are various problems. It turns out that not only these weak values, but these probabilities also have to be measured. And if you count the total number of data that's available to us, if there are m post-selected states, n minus 1 into m complex data plus n minus 1 real data, and that must exactly match n squared minus 1, and that is possible only when n is even and equal to 2m. Therefore, this kind of weak value tomography doesn't work for the general n case, but the problem is open. Maybe some variant of this can give us a weak value measurement for arbitrary spin. Thank you.
Thanks very much for finishing in time. So we have time for questions, comments.
No questions.
Yeah, thank you so much for your talk. In the, you characterize that the pure state cases is a scalar potential like that. This is so you induce the metric to characterize that's the one-to-one corresponding weak value and also that's the metric component. But in the mixed state cases, it is possible to extend such kind of concept?
Well, you know, I have a little problem hearing, so half of your question is registered, and so maybe during the break I can, you know,
Yeah,
discuss
right.
with you.
Hmm?
Thank you. I can come closer to you.
No, other people should hear. So, but to know whether a state a priori, since we have looked at the tomography and weak value, so look to first know the state whether it is pure or mixed itself, then that would be an important issue to decide before you go for.
You mean, so here, if you give me a mixed state,
Oh,
I'll
so
tell you a
if it is
tomography.
known to be mixed state. And another question in your one of the slides, you mentioned about weak measurement without post-selection.
Right.
So what do you mean by that? That is not used in your
So
discussion
this is in fact
subsequent.
the first weak measurement Aharonov used,
Oh.
where the measurement interaction or whatever you want to say,
Weak
it is
interaction.
weak, so there is no post-selection. If you want, you can think of it as averaging over every possible post-selection, okay? So you can call that the weak measurement, and it gives the expectation values by looking at the average value of the pointers, but there is no post-selection as such.
So I have a small question regarding the motivation for the last part. I mean,
Yeah.
I can understand weak tomography, weak measurement. What is the point of weak value tomography? Why does
Because, you
one-
know, you could do it for the pure case, and so one wants to see whether you can do it for mixed states also with weak value tomography. That's the idea.
What do we gain from weak value? I mean, I think,
Pardon?
what do we gain in special from weak value as opposed to just weak tomography?
Same thing in the pure case also. It's a new form of tomography. Okay, for example, the geometry of state space in these coordinates, you know, gives you a new way of looking at state space, trajectories in them, and so on. Okay. So these coordinates are measurable, unlike complex projective spaces, which is a mathematical object, and coordinates there don't have any necessarily measurable significance.
Okay, any other questions or comments? If not, let's thank the speaker.
Thank you
once
very
again.
much.